Alright, so let's start. So today we are going to discuss about a class of converters called modular multi-level converters, abbreviated as MMCs, modular multi-level converters. So before we go into this topology, we want to motivate the reason why this topology came into existence. So this is a half bridge based single phase inverter, and the load is connected between the midpoint of the DC bus and between the two switches. And when the top switch is on, the voltage here will be VDC over 2 with respect to ground. When the bottom switch is on, the voltage here will be minus VDC over 2 with respect to ground. So let's assume there is an anti-parallel diode to each switch. So whatever current was flowing into the load, say IL, must either flow through this branch or through this branch. So if the polarity is like that, the current flows through that branch or that branch. And one more thing to be noted is that the current does not flow through both these branches. Do you agree? When the top switch is on, if the polarity is that way, this switch conducts the current and this switch is off, so this takes no current. When the bottom switch is on, probably the diode takes the current, but the top branch does not take the current in that case when the bottom switch is on. So what we need to see is that only one of the two branches take this load current, and the output voltage, if it's decided to be made sinusoidal, we do PWM. We connect the top switch for some time, bottom switch for some time, and create an average voltage here depending on the times for which the top and bottom switches were on. We know this, right? We saw this in 4741. So suppose this voltage was required to be sinusoidal like that with respect to ground here, with respect to midpoint of DC bus, then probably the maximum time for which the top switch would be on in any switching cycle would be at this point. Would you agree? So what I say is, if let's say VO is sinusoidal like that, the maximum time for which the top switch would have been on in a switching cycle would be at this point, because this is the maximum average voltage that we need to produce. Similarly, the maximum time for which the bottom switch would have been on would be at this point. Okay, the output current is again sinusoidal, probably with a phase shift, because there is an RL load here. So VO is this waveform with an average of 0 with respect to ground. Okay, but what is VO with respect to N? Let's say this is G. Okay, so VOG is has an average of 0. What about VON? How will VON look like? Let me take another page. So VOG has an average of 0, VON has an average of VDC over 2, right? If this is 0, we have VDC over 2 and we create a sinusoid. Okay, so that's the basic half bridge inverter. Now let's look at the circuit and assume this is say 300 volts. VDC over 2 is 300 volts and this is 300 volts. Now this is all fine. What will happen if the total VDC is say 100 kV? Okay, what will happen if it is 100 kV? Will this circuit as such, is that feasible? It's not feasible, because we know one of the switches is on at any time except during dead time. When there is dead time, still only one of the branches will conduct the current depending on the polarity of the current. The current is outward, this diode conducts. The current is inward, this diode conducts. Okay. So coming back to 100 kV, for 100 kV this topology, this circuit is not feasible, because when S1 is on, S2 is off, the voltage across S2 is VDC, right? This point is N and all of VDC applies across S2. When S2 is on, the bottom point of DC bus is connected to the output point, and S1 sees a voltage of again the whole of VDC, which is 100 kV, and to date no switch can block 100 kV voltage. The maximum voltage that a switch can block is about 4 kV, maybe in SiC based switches. So that's why we need MMCs. MMC is come into play when the DC bus voltage is, say, more than 10 kV. Okay. But even before going to MMC still further, we can argue that we can connect switches in series. Okay. So suppose this blocks 4 kV and we need it to block the full DC bus voltage when S2 is on. How many switches do you think we will need? Each switch blocks 4 kV and we need 100 kV. If we need to block 100 kV, so how many switches would we need? 25 switches, right? 25 switches. So let me draw that circuit. So if I draw 25 switches in series like that, okay, the dot 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 represents the remaining 21 switches. Okay. Okay, so again we have the output connected between midpoint of the DC bus and the midpoint of this array of switches. Okay, so there are 25 switches in here, 25 switches and 25 here too, and this DC bus voltage is 100 kV. Okay, so this 50 kV, 50 kV. Now each switch is 4 kV and that is still feasible, but there is another problem with this. Suppose we want to create this VO through PWM. So when we say PWM, let's create the PWM switching pattern for a sine wave at VO. Okay, so we have VO. VOG, let's say this is G, and VOG is a sine wave like that. So how will the PWM pattern look like? I am drawing the PWM pattern for S1 in this circuit. Okay, S1 in this circuit. It will be, suppose this is one switching cycle, let's say 1 TS, and we want maximum time for which the switch S1 is on at this point. So we have almost 0 time when it is off, and almost full time of TS, all the time during the TS S1 is on, and then during this portion S1 is again, let's divide a portion TS. So maybe it's just a line here, it's on only for one time, and then maybe the pulse width keeps increasing like that. Okay, and then it just becomes a line there, and here. So actually it's not a line here, because at this point it's an average of 0. Okay, so for an average of 0, S1 and S2 would have been on for the same amount of time, but during this point S2 would have been on in a switching cycle for maximum time. So it is during this time that it will be a line. So here it will still be a small pulse, so maybe it should be like that, and at this point S1 will be on for the least time. Okay. So as we proceed like that, the pulse of S1 becomes narrower and narrower and narrower, and again maybe it increases a little bit. Okay. This is a pulse for S1. All right. So why I was saying this is that if you look at this circuit, we know that to create the same PWM pattern, to connect VDC over 2 at this point, we want all the switches to be on, right? Before it was just S1. Now we need all the 25 switches to go on. So at this, during this pulse duration, all of 25 switches would have been on. During this duration, all of 25 switches would have been on, but only for a smaller time during TS. So suppose it has been on for so much time and it wants to turn off, then all the switches should turn off, right? And they should turn off synchronously. What will happen if one of the switch doesn't turn off? Or if one of the switches turns off faster than the others? Then suppose all these switches are on, okay? Suppose all these switches are on and this switch is off and all these switches are on. So only this switch is off. So in this case, this switch will now have to block all of 100 kV. So it will fail. Okay. And the other problem is these switches in series, 25 switches, may not have the same on-state resistance. So the blocking of the voltage will not be even. Some switch may say see 6 kV, some switch may see 4 kV, so then we need more number of switches than the maximum 4 kV for it not to fail if the resistances are different and voltage sharing is. So we need additional voltage sharing circuits for these series connector switches. And then another problem is the harmonics in the output voltage. So to create VO of sinusoid, we need to create this pulse pattern. Okay, this pulse pattern will in turn mean so this is PWM S1. Let's plot VO n instantaneously, not on an average basis. VON on an instantaneous basis, not average basis, will be what? Just like the pulse pattern, except that the pulse, so ones and zeros will be converted to VDC and 0 because it is with respect to n, okay. So when S1 is off, S2 is on, here when this portion is on, then output voltage is 0 with respect to n, right? So the pulse pattern will be VDC and 0, like that. So this is VDC and 0. So what I want to drive at is the pulse pattern, the average voltage of the sinusoidal average that needs to be created is created by pulsing or switching between all the way up to VDC and all the way up to 0. The problem with that is, first of all, if this was connected to a transformer, it would see a large dV by dt. So instantaneously the voltage the transformer sees will jump up to 100 kV and jump down to 0 kV, which is very bad for transformer insulation. So do you follow what I mean? So when it was 0 and suddenly at the next moment it's 100 kV, and the PWM happens at very high frequencies, say 10 kilohertz for creating a sinusoidal, right? Sinusoidal average. So dV dt is high, and series connected switches, voltage sharing. So the first, so the dV by dt is a problem. Series connected switches, voltage sharing is a problem, and another problem is the harmonics at the output voltage. The harmonics that we see here will be very high in case of series connected switches. In MMCs, as we will see, so if we do a PWM with say 10 kilohertz PWM, then the first harmonic will also be at 10 kilohertz. But in MMCs, suppose we had 25 such switches. In MMCs we have modules instead of switches, as we will see. But if we had 25 such modules in one arm, 50 modules in the whole leg, the first harmonic, so this is PWM in case of series connector switches. So PWM with 10 kilohertz in case of series connected switches is like that. Let me write it here. So we have a dV by dt problem, we have a series connected switches problem, and harmonics. So the first harmonic in case of MMCs, instead of being at 10 kilohertz for 10 kilohertz PWM, it will be at 50 times 10 kilohertz, the first harmonic. So much purer sine wave in case of MMCs. If we have 50 modules in a leg. Okay. So that is a motivation to go to MMCs. Now we are all done with the motivation, and let's just dive into MMCs. Okay. Let's look at some simulation results. All right. So, so I have run the simulation. So before going to the simulation, I need to show you how an MMC looks like, right? So how does an MMC look like? It looks like this. So this is an MMC. We have, as I told you, instead of series connected switches, like here, we had a series connected switches here, right? Instead of that, we have these submodules which are not always series connected. What I mean is, not all of them are on at any time, not all of them are off at any time. Some of them may be on, some of them may be off. Okay, so there are these submodules, and each submodule is a half bridge. It looks like this. So the half bridge is so the half bridge looks like this. So there is a capacitor at the DC link, and there are two switches like that. So S1 and S2, and the output is like that. Okay, so so that is each submodule. This is one of these submodules. Okay, and how they are connected to each other is maybe not apparent in this, but I will draw it out here. So how are these submodules connected? So I have one submodule here, okay, and another submodule here, and let's say there are only two submodules per arm now, and this is the DC link, okay. So like that, okay, and then I take the output here, and then this point should be there, and so that's how they are connected. So I take the output of each half bridge, and I messed it up. So Okay, this is our MMC. So each module is a half bridge, and we have 2 submodules per arm. This is an arm. This is another arm. This whole thing is a leg. And 2 submodules in the bottom arm, and the output is connected between, say, the midpoint of DC bus and the middle point of this array of submodules. Alright. So this is an MMC, and that is what is shown here in 3-phase form. So there are 3 phases, and the submodules connected like that, and there is a small point of arm inductor that I missed out to draw here. There are arm inductors here, the reason for which we will go into, and yeah, so that is an MMC. So instead of this output voltage switching all the way between VDC and 0 with respect to N here, what will happen is some of these submodules will be inserted and bypassed. So then this voltage here will be, say with respect to ground, will be VDC by 2 minus the voltage of the number of submodules that are inserted. Okay. Yeah, I need to talk about this before I go into simulation. So, okay, let's. We need an output of, say, VDC over 2 and minus VDC over 2 at the output here, VO with respect to ground. Okay. So we need a sinusoidal voltage of VDC over 2 to minus VDC over 2, and each submodule, okay. Each submodule will be rated for VDC over 2. Do you know why? See, if, let's say why it is why each submodule should be rated for VDC over 2. So suppose both the bottom switches here are on. Maybe I need to talk about how. So I need to talk about the 3 states in which this. Yep.
So it's not totally apparent to me how this design solves that problem you were talking about earlier.
Yes.
Some of the switches need to block the entire thing.
Yeah. Thank you for the question. So how? Maybe I can draw. So our submodule looks like this. Okay, and we have okay. So let's say this is S1 and S2. Instead of series connector switches, we connect the switches through a capacitor across each pair of switch. Okay, that much is apparent, right? How does it solve the voltage blocking problem as compared to what we had earlier? Now, what blocking voltage does each switch see is the question. So when S1 is on, the voltage that S2 sees will be this capacitor's voltage. Similarly, when S2 is on, the voltage that S1 sees will be again the capacitor voltage. And then we can have as many number of modules as we want, and the voltage of each capacitor will go down proportionally. Now, suppose this is S3 and S4. Okay. Suppose there is suppose we wanted S3 and S1 to be on, but somehow S3 turned S3 turned on first before S1. Okay, so in that case maybe S2 was on. So what did we have earlier? We had this switch arrangement and output here, and suppose all of them were on, and this turns off first compared to others, then the voltage that the switch will see will be full of VDC. Similarly, suppose we had that S1 and S3 were on. That means both the modules were inserted. So both the modules are inserted, and suppose S3 turns off first and S4 doesn't turn on. Now only S1 is on. Okay. In that case, S2 will still see VC, and if both switches are off, there is antiparallel diode across the switch, and depending on the current direction, one of these will conduct, but still the voltage across the switch will be VC, which is here. Alright, so that much we know that it solves the voltage sharing problem and the voltage that each switch sees. Okay. Now, before we go into the simulation, we need to know how this output voltage is produced here. For that, we need to understand what inserted and bypass means. Okay, inserted submodule inserted means the top switch is on in each submodule. In each submodule's top switch is on. That's what inserted means. Bypass means bottom switch is on. Okay, that's as simple as that. And then what happens when both switches are off? Energization state. So there is inserted, there is bypassed, and that's all we use in simulations and practically everywhere. Energization is only during the startup of the MMCs. And the interesting fact about energization is that if both say S1 and S2 are off, S1 is top, S2 is bottom, let's say, this is bottom. If both are off, then the capacitor cannot discharge. None of the submodules capacitors can discharge. They can only charge depending on the polarity of the current. They may either charge or they may not charge. The charge may remain constant, but they will not discharge. See, for example, if okay, so if S1 and S2 are off and the current direction is say like that, okay, which diode do you think will conduct? This diode conducts, right? When the current direction is inward like that. Do you follow? So when this diode conducts, the capacitor charges. What happens when current direction is outward? Let's say current direction is outward like that. Then which diode would conduct? When both switches are off, the bottom diode would conduct, right? In that case, the current would just go like that. It doesn't involve the capacitor. So when both switches are off, the capacitors, none of the capacitors can discharge, they can only charge. The same thing happens in bottom arm too. Suppose the current was inward like that, and I have diode like that, and diode like that. If both switches are off, which diode would conduct? This diode would conduct, right? Capacitor charge. If the current direction was like that, this diode would conduct, and this capacitor will be bypassed. It will be like that. And if the current direction is outward like that, we have another diode here, and that diode would conduct, and it will miss the capacitor again. Okay. So those are the three states of each submodule. but we are only interested in inserted and bypassed, okay, those two states. Now, how do we produce this output voltage here? Let's say, let's consider the simple case. Let's give numbers so it's easier. Let's say this is 5 kV, 5000 volts, and 5000 volts here. Now, I told earlier that the sum of these two capacitors should be as much as the full DC bus voltage. There is a reason for that, and we are going to look at what the reason is. Okay, so suppose this module is inserted. That means what? This capacitor comes in the path of the current. Inserted also means that the corresponding capacitor in the path of the loop. Okay, that's what effectively it means, insert. And bypass means the corresponding capacitor is bypassed. All right. So this is true for any current direction. What I see, suppose S1 is on and the current direction was inward, then the diode will take the current and capacitor is inserted. Similarly, so the current would go like that in this case, like that and like that. And here, depending on whether S3 or S4 was on, either this capacitor is again inserted or bypassed. Okay, but for now we know that if S1 is on, this capacitor is inserted, right? Definitely ask me questions and stop me if it's not clear. So when the current direction is inward and S1 is inserted, the capacitor is in the path, and suppose S3 was also inserted, again the diode conducts, okay, and the capacitor is again in the path. So both capacitors are inserted. Suppose the current direction was outward like that, then what will happen? Suppose S1 is inserted again and current direction is outward. Listen carefully. So if current direction is outward and S1 is inserted again, so S2 cannot take the current, right? So there is no path there. So the current goes through the capacitor and out through the switch and out through the DC link. So in that case, the capacitor discharges. So let me write this down too. So let's call this current IU, okay, IU. So when IU is positive, IU greater than 0, then if S1 is on, then what happens? What is IU is that direction, like that. This is IU. Okay, let's take that convention. When IU is positive and S1 is on, what will happen to the charge through capacitor? Capacitor discharges, right? And when S2 is on, nothing happens. Capacitor stays same, charge constant. Okay. When IU is less than 0 and S1 is on, IU is less than 0, current goes like that, and S1 is inserted, capacitor charges. So capacitor charges, S2 is on, nothing happens. S2 is on, capacitor charge remains constant. Okay. So we know that. Now we need to produce this output voltage here, and we need to produce. Okay, let's see. Let's assume both these submodules are bypassed. Okay, both these submodules are bypassed. Then what do you think this voltage will be with respect to ground? Please help me here. So when both submodules are bypassed, what will be the path? Path of the current will be like that through the bottom switch. Capacitor is missed, right? S2 is on. Whatever be the direction of the current, if the direction of the current is inward, S2 conducts, outward diode conducts. Okay, let's assume the current is into the capacitor, okay, into the submodule. Let's assume that and follow the path. Okay, so the current is like that. So let me make this diagram little neater. let me take this off. Okay, let's see. So what happens when both modules are inserted, okay, and the current direction is outward like that, okay. So when S1 is inserted and the current direction is like that, when S1 is on, either the diode conducts or S1 conducts and the capacitor is inserted like that, okay. Because definitely S2 cannot take the current, it is off, and that diode cannot anyway take the current because the current direction is inward. So do you follow? So this diode should take the current and the capacitor is inserted, and now the current goes like that, and let's say S3 is on again, the same thing happens, the upper diode takes the current and the capacitor is inserted again, okay, and and this point is connected, and then what happens to the current from there on we should see, but we are interested in the voltage here for now. So neglect the drop across the arm inductors, okay, and assume both modules are inserted. Okay, what will be the voltage here with respect to ground? So if you follow this loop, like that, so VO is this voltage, okay, this is VO. So VO will be 5000 minus this module's voltage minus this module's voltage. So let's see. So VO in that case will be VDC over 2 minus VC minus VC. Okay, all right. Suppose both modules are, so this is S1 and S3 on, inserted, inserted. Okay, what will happen when both modules are bypassed? Say S2 is on and S4 is on, bypassed and bypassed. In that case, what will VO be? VO will be VDC by 2, no drop here, right? No drop here because the current is inward and this switch takes the current, no drop here and the current flows like that. Is it clear? Let's see, we'll erase this off. Okay. Okay, so current is like that and S2 is on, so S2 takes the current, the switch takes the current and goes like that, alright, and then goes like that and S4 is on again and S4 takes the current again, and this point's voltage will be VDC over 2, VDC over 2. So when both are bypassed, when both modules are bypassed, we have a maximum of VDC over 2. So don't you think that so this is the maximum positive voltage, and for a symmetric sine wave, if this point is VDC over 2 with respect to ground, so this is VOG. So when both are bypassed, we have maximum positive voltage of VDC over 2. So don't you think we need a maximum negative voltage of minus VDC over 2? So in that case, what do you think the sum of these two voltages will be? Exactly. So VC plus VC should be equal to VDC. So that is why we need the submodules to be rated at VDC over 2. If we have only 2 submodules. So what is the general formula? General formula will be number of submodules per arm. Let's call N to be number of submodules per arm. In that case, N times VC should be equal to VDC. Okay. All right. So let's look at 2 more cases. Okay. So we know what happens when both are bypassed. We know what happens when both are inserted. What if S1 is inserted and what if SM1 submodule 1 is inserted and submodule 2 is bypassed? What will be the voltage here? Can you tell me? I'll let you think. So we want the voltage. What is VO? VO equals what when SM1 inserted, let's call I to be inserted, SM2 to be bypassed. What will be the voltage? Is it 0? I don't know, I have to check. But is it 0? Did you all figure that out? So let's see. So when this is inserted, I have a drop of VDC over, yeah, it is 0. It is 0. So output voltage is 0. What happens when SM1 is bypassed and SM2 is inserted? VO equals 0 again. That's it. We have all covered all the four. So then to create the sine wave, one way would be like this. Okay, I've only been looking at the upper arm. We should do something with the lower arm too, but we will get to that. But let's assume that VU is produced only due to the action of the upper arm for now. In that case, how will I produce the sine wave? I will produce this sine wave like this, right? So I need this sine wave, and how many levels do I have in my hand? I have a level of 0, I have a level of 0 again, I have a level of VDC over 2, I have a level of minus VDC over 2. Is there anything else that I have with me? I don't think so, right? So then I know what I will do here. I will produce minus VDC over 2 here, and then plus VDC over 2 here, okay, and then I also have a 0 level, so maybe I'll do 0 here, maybe I'll do this, okay, maybe I'll do that, but I will not do this. Maybe I'll switch between VDC and 0 and minus VDC and 0 in these two half cycles to create an average, but this is okay, this is still okay. It has higher harmonics, but still the fundamental may be the same. The fundamental will be a sine wave, approximately a good sine wave. Now, not a very good sine wave, but yeah, that is one way to do the PWM. So what happens with the lower arm then? So let's write a formula for the output voltage based on this. So we have VDC over 2 minus, let's call the net voltage produced by all the submodules, whether they are inserted or not. Let's call that net voltage instantaneously to be VU. Okay, so let me call that to be VU. So let's call this voltage to be VU. Okay, so VDC over 2 minus VU minus, there is an arm voltage drop. I can include the arm voltage drop. Yeah, let's ignore that for now. Okay, let's consider the simple case. So VDC over 2 minus VU should be equal to VO, right? And then in the lower arm, what happens is, let's call this voltage to be VL. Okay, what happens in the lower arm? It's VL minus VDC over 2. Do you follow that? So what is the voltage here? Suppose both are inserted, then it will be this voltage plus this voltage minus this voltage. Isn't it? Is that clear? See, so when so let's say this is inserted and this is inserted, then VC plus VC minus VDC over 2 is VO. What happens when both are bypassed? It is minus VDC over 2. Okay, let's see. So that is VL minus VDC over 2 is VO. So when both are bypassed, VL is 0. When both are inserted, VU is VDC. When both are inserted, VL is VDC. See, when both are bypassed, we know for sure that VL is 0, right? So we have a maximum negative voltage of minus VDC over 2. We need a maximum positive voltage of VDC over 2 too. So VL when both are inserted should be VDC, right? Just like we had in the upper arm. So this is the equation for the lower arm. This is the equation for the upper arm. But so how will you solve for VO from this? So VO is what? It's VL minus VU by 2, right? VL minus VU by 2. Now, so okay, I'm going to rub all this off, and I want to show you another way to produce this VO. We have lots of time. So I'm going to rub all the writing off, okay? Okay. So now consider the arm inductor drop. The arm inductor is not just the arm inductor. There is a resistance there too. Okay. Now the equation will be like this. So suppose the current direction. We have to assume a current direction. We can assume a convenient current direction. I will rub this off. Okay, let's assume IU to be like that and IL to be like that. Okay, so this is an RL branch actually. And similarly, an RL branch here. Okay, so now the equation will be VDC over 2 minus VU minus IU is like that. So L DIU by dt. Let's call this L arm minus IU times R arm is equal to VO, okay, and again VL. So what is VU and VL? VU and VL are created due to sum of submodule voltages, depending on how many are inserted or bypassed, function of I and B. Okay, so VL minus VDC over 2. So IL is like that. So IL is like that. So what will be the so polarity of this drop was like that. Polarity of this drop will be like that, and VL is like that. So I have and I. Okay, so minus VDC over 2 minus VL plus is equal to VO. Okay, so it will be, so how is the equation? So it will be minus VDC over 2 minus VL plus, so minus VDC over 2 minus VL plus R arm IL plus L arm DIL by dt equals VO. Okay, so this becomes plus VL. Okay, so add 1 and 2. Okay, add 1 and 2. 1 plus 2 becomes VDC gets cancelled, and we have VL minus VU. Okay, so IL and IU. We need to find a relation between IL and IU. So when I showed you the half bridge, I said that only one of the branches takes the current, output current. But here both the branches take the current, and suppose IL is like that, it divides equally between, approximately equally between upper and lower arm. Okay, so let's say IL over 2 flows like that, and IL over 2 flows like that. Okay. So definitely IU has a component. IU has a component minus IL by 2. IU has a minus IL by 2 plus an IC component. What is IC? We will get to that. IC is the circulating current. Circulating current circulates like this. That's IC. Okay. We will get to that, and we will get to how it is created. But take it from, so on an average, IL splits equally between the upper and lower arm. The reason will become clear in a little while, but let me finish this equation. So take it from me that IL splits equally between upper and lower arm like that, and half of it goes like that, half of it goes like that, and I have assumed IL to be of this polarity. So IL will be what? IL will be minus IL by 2 minus IC. Right? IC flows like that, IL over 2 flows like that, so IL is minus IL over 2 minus IC, right? So then, okay, so this is an equation, this is an equation, this is IC, I circulating, let's say I circulating, and if you plug in these two here, plug in for IU and IL over here, and we are adding those two, right? We are adding equation 1 and 2, and IU and IL have a common component which is I circulating, and when you add these two equations, that cancels out. Okay, so and then we have common, so IU is downward, IL is downward, IL over 2, I circulating. VL minus ADC over 2. So if I plug in minus IL over 2 here, yes. So I circulating component cancels out. Do you agree? IG over 2. Let me see. VDC over 2 minus VU and minus VDC over 2 plus VL. These two should be of the same sign. IP and IN. I differential. Yeah. VL minus so if I add 1 and 2, I get VL minus VU plus I circulating component is the only thing that remains, because these two are of opposite sign, and I circulating is of opposite sign. If you plug in that, if you plug in these two equations here, you get R arm I circulating minus R arm I circulating minus L arm d I circulating by dt 2 times this is equal to 2 VO. Okay. All right. So what is VO then? VO then is 1 by 2 of this. Okay, so we have approximately VL minus VU over 2, but just a difference of the arm resistance and inductor terms. So then so we did that. Thinking why we did that. Oh my God. Okay, so so do you see that there is a net voltage produced here and a net voltage produced due to this branch? So the voltage produced here is so if we call this VU, if we call this VL, the voltage produced due to the upper loop till ground is minus VU plus VDC over 2, right? And the voltage produced due to the lower arm is VL minus VDC over 2. And the voltage here is the average of those two voltages. What I mean is, see, okay, let's write this off. So minus VU plus VDC over 2 is VO, and VL minus VDC over 2 is VO. And what will happen if you take the sum of these two and divide it by 2? That's the average, right? That is the output voltage. So voltage produced here is the average of the net voltage due to this loop and net voltage due to this loop. All right, that is a good takeaway. So the thing is, you have two voltage sources connected to a common point through an arm inductor. So what will be the voltage here? It will be average of those two voltages, right? Do you follow? So what I say is, I have this voltage and another voltage here and connected like that. What will be the voltage here? This is V1 and V2. It will be the average of V1 and V2, right? The same thing is happening here. So this arm inductor is like this, these two arm inductors, and V1 and V2 are the net voltage produced due to VU and VDC over 2 and VL and VDC over 2. So the average there will be minus VU plus VDC over 2 and VL minus VDC over 2, the average of those two. So then what we will do now is use these voltages VU and VL to create an approximate sine wave here using PWM. Okay, so that is all I wanted to say. So now I want to go to simulation.
Quick question.
Yes.
So if you add more branches to the arm.
More submodules.
Modules. Thank you. You basically can create a more precise sine wave. because you have more levels of voltage?
That's correct. That's exactly correct.
Okay.
That's exactly correct. Because here when I do the approximate sine wave, we have only 3 levels, right? If we have more levels, we create a smoother sine wave. That's correct. Yes.
Is that IL correct?
IL. So let's see that. So I assumed that IU was like that, or what did I assume? Did I minus? So I assumed IU was like that, and IL was like that. Okay. So what is IU? IU is my
You were assuming IU was the opposite direction.
Okay. IU is like that, and IL is like this.
No, I think it, or what?
Uh,
They were both coming in.
okay, they were both coming in. Good.
And
Okay.
IL was,
Outward.
they were all going in towards the VO node. So
Ah.
IL was going the opposite direction too.
I see. Yeah. So I think so. If you assume this polarity, IU, IL, and they add up to IL, I load. Okay. Now, what is IU? Please help me. IU is plus IL over 2, right? Plus IL over 2, plus I circulating, right? So I circulating is like that. I circulating flows through the leg from the DC link like that. All right. Do you follow? I circulating is like that. It is some current whose cause we don't know, but I will tell you the cause. But I circulating is like that, and also assume I load splits equally between these two. Why they split equally is very easy actually, because VU and VL almost produce the same average voltage. You see, so let's say VU is A sine omega t minus A sine omega t. This is VU, and VL is A sine omega t. Okay. Okay, and then VO will be what? VO will be VL minus VU over 2. That will be A sin omega t. So VO will be A sin omega t also. Okay. So VL and VO almost produce the same average voltage, same sinusoidal voltage, and that is why I load splits equally between the upper and lower arms. So I load goes like that. IU is I load plus I circulating, and IL is what? I load minus I circulating. Okay. I load minus I circulating. Now what happens? Again the same thing happens, right?
Yeah, now it's
Okay. Yeah. So yeah. Yes. So we know how to produce the output voltage here using PWM of the upper submodules and PWM of the lower submodules to create a sine wave here. So so what will be the waveform of VU? What do you think? How will it be? I know this equation, right? Just think about this equation. If I draw the waveform of VU, how will it look like? How do you think the waveform of VU looks like? So I need an output voltage. So this is output voltage. So I know my output voltage is a sine wave, and I know I have to I know VU is in the opposite direction to VO. I know that, right? Minus VU plus VDC over 2 is VO here. So VO and VU are in the opposite sense. So I know my VU will look like that, but I also have I also subtract VU from VDC over 2. So VU should be at a DC of VDC over 2. So with this waveform, if you apply this equation, do you think you get VO? So do you see what I'm getting at? So VDC over 2 minus VU. So VDC over 2 minus VU, VDC over 2 cancels out, and minus VU is VO. Similarly, what do you think VL will look like? VL will look like, again it will have a DC of VDC over 2 because we need to cancel that out, and then it will be a sine wave. So it will be like that. Okay. So when we do PWM, what will we do? We will give a positive sinusoidal reference to lower arm submodules, a negative sinusoidal negative of that sinusoidal reference to upper submodules, and create the output voltage. Okay. So that's it, and yeah. So what we have here, if you can see, is 4 submodules in one arm, and there's an arm inductor, again an arm inductor, and 4 submodules. Now this block is capacitor voltage sorting balancing block. Please ignore that for now. Why we need that block is because we want all submodule capacitors to be at equal voltages. So at every switching instant, when we want to insert a bypass module, we look at which is the lowest submodule in charge and insert that if the current would charge it. Like I drew those equations there, right? If IU was positive and if, so that is what the block does. Okay, forget about that block for now. Now, let's see. Let's look at this. So this is the sine wave generator, and there are many carriers here. So there are how many carriers? There are 8 carriers, and each carrier is for one submodule. There are 8 submodules, right? 4 submodules per arm. So each carrier corresponds to one of the submodules, and the carriers for each of the submodules are a little different from each other. They are different in the sense that they have some phase shift between them. We will come to that, but all those triangles are taken here. 4 triangles for the upper submodules are taken here. 4 carriers for the lower triangle are taken here, and we have a sinusoidal reference which is negated to the upper submodules because of the reason we just saw, and given access to the lower submodules. Okay, because we know VDC minus VU is VO. So we need to produce VU with the opposite polarity as output voltage. So this block actually produces the output average voltage, right? So the average voltage that we produce should be in the negative sense of output voltage. That is why we give a negative here. Do you follow? So we have that equation, right? VDC over 2 minus VU is VO. So VU should be of the opposite polarity with the output voltage. And so we give the reference as such to the lower set of triangles. And this summation blocks compares triangles with the sine waves. So if it's greater than 0, it means the triangle is bigger. If it's less than 0, it means the sine wave is bigger. If the sine wave is bigger, we give a switching pulse of 1. Otherwise, we give 0. But this is just a detail of Simulink, which is not very important now. All that we need to know is if the sine wave is bigger than triangle, the switch is turned on. And we give the same triangle reference, sine wave reference to each submodule. Only the carriers are different. Okay. So in order to produce this net VU, okay, how much do you think the average voltage of each submodule is? It's VU over 2, right? An average of VU over 2 because these two add up. So average here and average here add up, and so the net sine wave produced will be sine wave average due to this plus sine wave average due to this. Okay, so so at the output we have an average of VDC over 4, right? And VDC over 4 here and VDC over 4 sin omega t, VDC over 4 sin omega t, they add up to VDC over 2 plus VDC over 2 sin omega t. So all that I want to say is this net sine wave average is produced by the sum of the average voltages at these two modules, because the voltage here is like that, which is added to voltage here. Okay, that's all I want to say. Right. So what can I show you? I can show you the output voltage waveform. That will be a good idea. I run this again. Let it run. We have a couple of minutes. A lot of interesting simulation results to be seen. What my plan was to show you only simulation results and explain you why they are the way they are. But in order to know how we create this output voltage as a sine wave, we need to know that some modules are inserted and bypassed to create an average sinusoidal voltage. So you know what will happen for creating the output voltage like this. We will have levels, as you said. So let's look at this. Okay. So what will happen is we will have this is minus VDC over 2, right? When will we get minus VDC over 2? When both are bypassed, right? So here it will be almost 0 modules on and maybe 1 module on, like that. Okay, and here what will it be? It will be 1 module on and 2 modules on, like that. Do you follow? So when we wanted minus VDC over 2, we wanted both modules to be bypassed, right? Right? So when we want to create an average around minus VDC over 2, we want either 0 modules on for minus VDC over 2 or 1 module on to create an average around minus VDC over 2. To create a little higher average, what do we need? We need 1 module on or 2 modules on to create an average corresponding to a voltage between those two submodule levels. So if only 1 module is on, what will happen? It will be minus VDC over 2 and only 1 voltage will be subtracted, right? So that will be almost minus VDC over 2 if you have large number of submodules. So as we want more and more higher voltage, we want all the modules to be so when the modules are bypassed, we actually have plus VDC over 2. When the modules are bypassed, plus VDC over 2 is connected to output. When we want 0 voltage, we want minus VDC over 2 voltage, we want all the modules to be inserted actually. Right? So VDC over 2 minus VDC is minus VDC over 2. When all the modules are inserted, approximate voltage is VDC. So it wouldn't be like this. But we are looking at VU. We are not looking at VO. When we are looking at VU is this voltage. That will be lowest when everything is bypassed. Right? Sum of submodule voltages is VU. That's more straightforward. We need not even look at VU. So this is correct. So this will be either 0. But yeah, in that case, this is not minus VDC over 2. It should be 0, right? It should be 0 around an average up to plus VDC. When all modules are bypassed, you get a 0 voltage here, right? So it will be either by 1 module bypassed, 1 module inserted, and then a little higher will be little higher voltage. So 1 module is inserted or 2 modules inserted, and go on, so on like that. Okay.
So why is there a module on at the lowest peak?
Oh, it won't be. At the lowest peak around TS, it will be bypassed. It will be bypassed all through TS. Only just around the lowest 0 voltage, we have an average of switching. All right. Yeah. Um, yeah, I think we are done. We have lots of simulation resource to see next time. Thursday. It's not in the university today, I think.